This is lecture 22 for Friday. What is that day? Friday, I guess, is going to be the 22nd. So I want to go over a couple of examples. The first one is this one to your right, which can be found on in the rigid body dynamics worksheets that I handed that are posted on Canvas. So if you look at the problem to the right, the problem to the left was done in, I believe, in another video, but the one on the right shows a bar AB that is on an incline of 25 degrees. It's connected to B, which is on a collar. Assume there's no friction. And in this problem, what's going to happen is B is going to be released from rest at the position shown, where the angle theta is 35 degrees, the angle A to the horizontal is 25 degrees, and that's all we know. So what we'd like to calculate is the angular acceleration alpha of the rod and the reaction at B. So this is a good chapter 16 problem in the sense as this would be about the difficulty level that you might see on the final. So I'd like to go through it. I've written it out ahead of time rather than frantically writing it for you because I think it might be a little easier. So I'm going to narrate it, but I would highly, highly recommend that you first pause the video and see how far you can get, and then pause, work, pause, work. This is going to be the greatest benefit that if you just watch me do the problem. So let's get to it. All right, so starting with this, what do we have? Um, so we know that the mass is 6 kilograms, the length is 1.5. So here I've just drawn it. G is my center of gravity, B here, that's the 35-degree angle. So I know there's an acceleration in the direction of B. There's also an acceleration of A down the incline, and this is 25 degrees here. Okay. So another way we can look at it is that as that bar is sliding down, it's going to have an angular acceleration I alpha. It's also going to have a um, acceleration of the center of gravity in the x direction to the left and down. So we're going to, for our coordinate system, we are going to make plus plus, meaning the normal negatives are going to be positives. One thing too to note is like other chapter 16 problems is at the beginning of the problem, omega is 0 because it hasn't started moving yet. So you can have acceleration without motion, just like you can have motion without acceleration. Okay, so first thing, let's think about. So acceleration of A equals acceleration of B plus the acceleration of A relative to B. Now, why are we going to do that? What we need is we want to establish the acceleration of the different parts so that we can ultimately find the acceleration of the center of gravity, because that's what we want in order to calculate alpha. So if I write acceleration A equals acceleration B, A relative to B, these are all vectors. Sorry about that. This is going to be kind of a scalar though, because we know that for any time that you write this out, B is your pivot point. Therefore, A relative to B is always going to be a perpendicular direction to your bar. Now we know our bar is 1.5 meters, so we can also write A relative to B is equal to R alpha or 1.5 alpha. Now, um, try to draw this triangle on your own if you can and figure out the angles. So pause here. Okay, so if you're not sure, how do I get this? I know AB is going straight down. I know that A relative to B has to be normal to this surface. So if you draw a line that's normal to that, then you know that this angle below here, sorry, this angle here has to be the same as this angle up here. And if I know that that's 35 degrees, then that's the complement has to be 55. I also know the acceleration in the A direction is at 25 decline, therefore its complement has to be 65, leaving 60 for this. So what this allows us to do, make this acceleration triangle. And what we can do now is we can use the law of sines and we could figure out that the acceleration of B with respect to alpha can be written as AB over sine 60, opposite angle, equals 1.5 alpha over sine 65. And that gives us the acceleration B being 1.433 alpha. Okay. So at that point, let's put up my screen. There we go. Sorry, I'm having technical difficulties. Make sure my zoom is correct. There we go. Sorry about that. Okay. So getting back to this. Now let's look at the next page. Now, what we're going to do with this is we're going to say, just like we could draw the acceleration of A relative to B there, like we did in the previous page, we can also write the acceleration of the center of gravity with respect to B is also going to be perpendicular. Okay. So now that you have that, you know, and we're going to say acceleration of A with a bar over it is representative of the acceleration center of gravity. Therefore, we know the acceleration of A equals acceleration of B plus acceleration of G relative to B. So that gives me B, which I figured out earlier is negative 1.433 alpha. Um, Now, I'm leaving it there. Actually, let's make it consistent. So I'm going to make that positive. Now, the reason and that should be because down is positive. So then I have plus, and now what this is this is 0.75 alpha, which is AG relative to B. Now, we know that AG relative to B, though, is pointing in this direction. So if I were to go back here and draw that, I know that's 35 degrees. Therefore, what I'm doing here, since I know that this was in the J, I have to make this in I and J components also. So using sine and cosine, I do that. So I know that the J component of the acceleration is up, so it's going to be negative based on our coordinate system. And when I add it together, I finally get my acceleration is equal to 0.614 alpha in the I plus 1.003 alpha in the J. Okay. All right. So now that we have that, let's look at a how we can determine the actual value of that. Now you recall that in order to do that, we're going to have to use that equation that you've used before that says the sum of the moments about a point is equal to I alpha plus MAD, perpendicular, right? So we've used that equation before. Now, in this case, we want to pick a point because we know any moments created have to be accounted for. And the best way is to, like we did in statics, we want to eliminate any unknowns. Now, if we look at this, we see that A, if we draw A, it travels at this angle 25 up to here. If we draw B, it travels in that direction to there. Now, this triangle is similar to the one we did previously for the acceleration vectors, but it's not the same. So if we look back on it, you can see that was just denoting the direction of the accelerations. This is denoting the direction of the reaction. So the big difference. So this would be more akin to statics, assuming there was no motion. So drawing this, just like we get the trig, same thing I did before using the angles. This one's probably a little easier to see. And then we're going to say that's equal to, this is my FBD. And here's my MAD. So that's going to look like what? I alpha, MAY, MAX, pointing those directions. Now, what I've done is I've drawn this little lines here. Those just represent dimensions. The reason I did that is because I want to take the moment about a point, and I'm going to pick the point E. Now, the reason I'm picking E, which isn't on the diagram, is if you remember in statics, if you had a couple of unknowns you want to get rid of, you could find a point in space where both of those unknowns crossed. And if I take a moment about E over here, then those disappear. Therefore, they're not going to be in this equation, and my only unknown is going to be alpha, so I can solve directly. Now, at this point, what I would recommend is figuring out the trig here, to take a time to do that, and then set up this equation as you think it would work. And I'd strongly encourage you that. So go ahead and pause, work on it, and if you get stuck, come back. Go ahead and pause. Okay, you're back. So I'm going to kind of leave it to you for the trig, but in terms of this EB, that can be found using the law of sines. Now you know the bar is 1.2 and you know the internal angles, so law of sines is going to give you these. DB here can be found by subtraction. And this is easy because we know this angle up here is 55. So we can use sine and cosine. We know this length BG is 0.75 or half of the total rod length. So this is basic trig. So I got these dimensions here. That's going to allow me to plug them into this. So if I do that, I get something like this. And hopefully you've paused and taken a look. So if I sum the moments about E, there's my I alpha plus MAD perpendicular, which really is what? If we look at our diagram, then the only force we have on this is on the FBD on the left side is the weight times the distance ED. And that would be this distance here. So ED is given. I got that distance. It turns out to be 1.003. So, and then that's going to equal I alpha plus MA in the X times DG plus MAYED. So just like before, we're just looking at the perpendicular distances of the accelerations with respect to E. So again, pause, write this out, see what you get. If you get stuck, here you can see I is 1/12 ml squared, which is a very common shape we'll use. So I would write that down in your notes. You don't have to memorize it, but it's going to be common enough that you'll probably will. So 1/12 ml squared, weight of 6 kilograms gives us 1.125 kilogram meter squared for I. And that's about, of course, the center of gravity. Now we know that acceleration can only be written as r alpha, where r is that perpendicular distance. So if we go ahead and put in our numbers here, we have the weight times gravity times the respective distance equals I alpha plus the weight times, now AX is what? I already have that earlier. I found out that that was equal to this. So I already have those values. The only thing I have to make sure of when I do this is make sure I keep track of the directions of the moments, right? Because this is the doesn't matter the direction of the forces, it's the direction of the moments. But it turns out that all these moments on the right side are in the clockwise direction, which I forced to be positive because just so I don't have a bunch of negatives. If you want to do negatives, that's fine too. You just have to carry them through. So I get the AX, AY, and of course, you could also write this, as I've said, is this is really the same as writing I plus MR squared times alpha, right? That's just the parallaxis theorem times alpha. So that's the same thing. We have 0.614 squared times alpha times the mass, right? So we get an answer 6.263 radians per second squared. We can then take those, plug them back into these values here, and we know our acceleration, the x and the y. Okay, so that's the first part. That was A. I was getting that. Now that we have that, we've done 80% of the work. And the next part is should be like statics in a sense, in terms of the way you set up your moment. So again, I would encourage you to pause and see if you can figure it out on your own. Okay, so if you got stuck at this time, we're not going to worry about taking a reaction at E because that would again, we wouldn't be able to find the reaction at B. That would get rid of both B and A. So we're going to take a moment about A because we're not asked about A. We really don't care. But because we only have two unknowns, we could find A once we found B, but we don't care about B. I'm sorry, we don't care about A because we're not asked about it. So what we're going to do is we're just going to sum the moments about A equal to I alpha plus MAD again. In this case, again, positive being clockwise, 6 times 9.81 times the distance. And of course, if we look at this again, now we're going this distance here from here to here, and basically this distance and that distance, right, for our respective accelerations. We know that B has a reaction that goes straight in, so it's going to be the entire distance to A. Okay, so hence we see the sum of the moments about A is going to be the weight times the distance, and then minus B times the entire distance times sine 55. That equals, so I ran out of space. So this here is that. Okay. This down here is all of this. So I have the I alpha, which we have. Then I have mass times acceleration in the y times its distance, and mass times acceleration x and its distance. And it turns to be a clock, it forms a counterclockwise moment. And since my positive is clockwise, I make that negative. And then I solve for B and I'm done. 13.22 newtons. And there you have it. Not so bad. Okay. All right. Now I'm going to do one more set of problems, and then by the time I get back, you guys will be experts in chapter 16 and we can just mop it up. Okay.